So hello everyone, welcome you all to live session 10 of NPTEL course Fluid Flow Operations taught by Professor Shubhrata Kumar Majumdar, and my name is Nagfan Saikama. I am the teaching assistant for this course. So last week we discussed about dimensional analysis and also law of similarity and significant dimensionless numbers. So this week we'll be discussing about compressible flow, so which includes dynamic characteristics of a compressible flow. We'll also discuss about the speed of sound or sonic velocity, and then we'll also look at something called Mach number, and then we'll also try to discuss and have an understanding of basic equations of dimensional compressible flow. Okay, so to begin with, compressible flows occur when the density changes are significant between 2 points on a streamline. Okay, so fluids have the capacity to change volume and density. So this we know, density and volume and density of fluids will be changed, be it with temperature or pressure. Okay, so and this phenomena is called compressibility. Okay, so the ability of fluids to change the volume and density is called as compressibility. And also, like as gas properties changes or the fluid properties changes, so compressibility also changes. Like the ability to get compressed also change, right? So when you compare liquid and gases, gas has large compressibility when compared to liquids. Okay, so not and also when we specifically take the case of gas, again depending on the characteristics of the gas, the compressibility will vary. So not all gas flows are compressible flows. Only those that have significant density changes are compressible. Okay, so again, when you compare with liquids, gases have higher compressibility factor or they are having more compressible nature. But again, even in gases, like there are different gases with whose compressibility will change with the nature. Okay. So, but when its velocity is lowered with the sonic velocity, the changes in density is small and it is then treated as a incompressible fluid. Okay. So we'll come to uh, this sonic velocity as well. We'll try to understand in the later slides. Okay. So coming to incompressible gas flow. So incompressible gas flow occurs when the density of air does not change more than 3% between the point of interest are consequently treated as incompressible gas flows. Okay. So let's say this is the final point and this is the initial and final point or maybe your point of interest. So let's say if the gas does not change its density, if you consider these 2 points, if the gas or air does not change its density by more than 3%, then this is considered as incompressible flow or incompressible gas. Just a second, someone is joining. Okay. So if the density changes are less than 3%, then it is considered as an incompressible flow. Okay, so we have many examples. One is flow around automobiles, okay, and flow in hurricanes, and then flow around aircraft during landing and takeoff. That is also considered as incompressible flow, and flow around buildings and communication towers. This is also considered as incompressible gas flow. Okay. So coming to compressible flow. Okay. So we already know that if the density change is less than 3% between two points of interest, then we can consider it as incompressible. So obviously, gases which are having more than 3% change are considered as compressible flow rate. So the gas flows in which density does change more than 3%, they are called as compressible gases or compressible flow. Okay, so examples again, airflow around aircraft that fly faster than 100 meters per second. Okay, whenever flight is landing and taking off, it is considered as incompressible flow. But when the aircraft is flying at such a high speeds, like 100 meters per second, then it is considered as compressible flow. And flow through compressors, jet engines, and tornadoes. So it is also considered as compressible flow. And then we also have another example that is there are also compressible effects in liquid flows that give rise to water hammer and underwater compression waves from blast. Okay. So these are different examples of compressible and incompressible fluids or incompressible gas and liquids. So how do you express this compressibility? Okay, so when you're saying a gas is getting compressed, so how do you express the compressibility? So let's say you want to express quantity of a gas. Okay, you can express it in number of moles, or you can also express it in terms of volume as well. Let's say you have 3 liters of liquid, or let's say 5 moles of gas. Okay, so you can quantify it, right? But let's say if a gas is getting compressed, how do you quantify the compressibility of that particular gas or liquid? So there is something called bulk modulus, using which this particular parameter bulk modulus will help us understand the compressibility. So how do you define bulk modulus? So it is defined by variable K, and K is equal to pressure change upon del V by V. Okay, so we can also write this as minus V into dP by dV. Okay, so this is called bulk modulus. So I'll also tell you how to calculate this. So let's say we have a container and this is attached to a pressure transducer or some kind of pressure measuring device, and then there is a piston or okay, there's a piston inside this. So this is connected here. Okay, let's say there's a piston inside, and let's say the initial volume is V and the corresponding pressure is P. Okay, so when you're applying some pressure on this piston, what happens? This will be moving through a certain displacement, right? So let's say the volume change is del V and the pressure change is del P. So the final volume will be V minus del V, and the final pressure will be P plus del P, because pressure is increasing and volume is decreasing, right? So volume will be V minus del V and pressure will be P plus del P. Okay. So from this you'll be able to calculate the bulk modulus. The change in pressure and change in volume, you'll be able to calculate the bulk modulus. Okay. So from there, there's something called compressibility factor, which is represented by beta. So beta will be equal to 1 by K, that is 1 by bulk modulus. So this beta will give us the, or will quantify the compressibility of a gas. Okay. So if you consider normal temperature and pressure, so at normal temperature and pressure or NTP, so for water, value of K is around 2.06 into 10 power 9 pascals. Okay. And for air at the same NTP condition, that is normal temperature and pressure, for air, compressibility factor will be 1.4 into 10 power 5 pascals. Okay. So if you observe, like we generally know that water is incompressible fluid and air is a compressible fluid, right? So as beta, so we as water is incompressible and air is compressible fluid, water should be having water should be having lower beta value, and air should be having higher beta value. Like when you compare both these gases or when you compare both these fluids, when you compare these both these fluids, beta should be lower for water and air should have higher beta value. So this means that K should be higher for water, right? Because they are inversely related, right? So K should be higher for water and it should be lower in case of air. Okay, so in relative terms. So that is what evident here. So beta is, so the K is higher in case of water and lower in case of air. Okay. I'll also give you a value of beta for water. So beta is 4.85 into 10 power minus 10 1 by Pascals. So just take inverse of this and you'll be getting the value. Same thing here. Just take inverse of this 1 by 1.4 into 10 power 5. So you'll be getting the value of compressibility. Okay. And how do you relate density and volume? Or let's say density and volume are inversely proportional, right? We can take PV is equal to nRT, okay? Or we also have another equation. So let's say if volume is increasing, what happens to the density? Density will reduce, right? So let's say if you have a container and you were having a piston as well, okay? So I'm entrapping the gas in this. Let's say there is some gas and initial volume is G and the corresponding density is rho. So in the next case, I'm increasing the volume of the gas. Okay, so let's say I'm increasing the volume of gas. So now the volume of the gas is increased. What will happen to density? Density will obviously decrease, right? Because density is equal to mass by volume. If volume is increasing, then density will reduce. So we know that this will remain constant. Okay, so this product will always remain constant. So instead of volume, here we can also write density because their product is always constant, right? So we can just write V is equal to m by rho and then substitute in this equation, in this particular equation. So we just substitute it, we'll be getting rho into del P by del rho. Okay. So we can also write this as rho into dP by d rho. So bulk modulus we can also calculate in terms of we can calculate using volume changes. We can also do it in terms of density changes as well. Okay, so we'll be getting the same value. And the mass term will get cancelled out. Okay, so here there will be mass term in this like when you're substituting it. So here you'll be getting a mass term, and here also you'll be getting a mass term. So as it is a constant, it will not you cannot differentiate the differential constant, right? So in both the terms you'll be having mass, and both of them cancelled out. So you'll be getting this equation. And we know that bulk modulus is closely related to the velocity of a pressure wave propagating in a fluid. Okay, so we can also relate it with velocity as well. So C will be so all these derivations are out of scope, so I'm not going to the derivation part. So I'm directly writing down the equation. So dP by d rho, which is equal to again if you can just substitute the variables. So from here you can write dP by d rho can be written as K by P, right? K by rho, right? So I'll just substitute it here. I'll be getting K by rho. Okay. So coming to thermodynamic characteristics, so a gas having the following relationship between absolute temperature and pressure. So we all know. So for almost all gases, PV is equal to nRT, like or RT. Okay, and R is R naught by M. Okay, this is so value of R naught is 8.314 or 8314 joule per kg Kelvin. Okay, so we generally use R naught here, but for real gases, it will be R, whose value is R naught by M. Okay, and where M is the molecular weight of that particular gas. Okay, so let's say if we take air as an example. So for air, its molecular weight is 28.96, right? So value of R will become 8314 by 28.96, which will be equal to around 287 joule per kg Kelvin. Okay, so if you and then assuming internal energy and enthalpy per unit mass as E and H respectively. So E represents internal energy and H represents enthalpy per unit mass. So then the specific heat at constant volume can be written as Cv is equal to del E by del T at constant volume. So you can also write as dE is equal to Cv dt. Okay, so this we already know. So this is one equation. And constant pressure Cp can be written as del H by del T. Okay, that is at constant pressure. And you can also write this as dH is equal to Cp into dt. Okay, and we also have a relation between H and E, that is H is equal to E plus PV. Enthalpy is equal to internal energy plus PV. So this is equation number 9. So according to first law of thermodynamics, when a quantity of heat, let's say dq, is supplied to a system, then the internal energy of the system will be increased by an amount of, let's say, dE, and a work is done, that is PdV is done on the system. So then you can relate all these variables using dq is equal to dE plus PdV. Okay, that means whatever energy you are supplying is used for increasing its internal energy and also to do work. Okay, and from equation of state we can write PdV plus VdP is equal to R into dt. So just integrate PV is equal to RT. Just integrate it. You will get this equation. This is equation 9, 11. And from equation 9, okay, from this equation, you can write dH is equal to dE. Just differentiate the equation. dH is equal to dE plus PdV plus VdP. Okay, this will be equation number 12. Okay, so in case of constant pressure change, dP will be zero because there will be no pressure constant. There will be constant because of the constant pressure change. dP will be zero. So in that case, equation 11 and 12, this will become zero, and this will also be zero. So in that case, it will become PdV is equal to RdT. This is at constant pressure. Okay, and the equation number 12 becomes dH is equal to dE plus PdV plus which is equal to again dQ. Okay, so from equation 7, 8, 11 and 12 we can write Cp minus Cv is equal to R, which is equation number 15. And now we also have a relation between Cp and Cv, so that is Cp by Cv will always be constant, that is equal to K. We can also write Cp is equal to K by K minus 1 into R, and Cv as 1 by K minus 1 into R. Okay, so all these relations you will be anyway discussing them in thermodynamics. Okay, so I'm just trying to revise these concepts, and We may also determine the entropy change or assume an isentropic process. That means change in entropy is zero. ds is equal to zero. So then one of the following equations can be used. That is, so let's say if ds is equal to Cp into ln T2 by T1 minus R into ln P2 by P1. So we can write T2 by T1 as P2 by P1. If at all ds is zero in this case, if at all we are talking about isentropic process, then ds will become zero. So then you can just simplify this equation to any of these forms. That is, T2 by T1 is equal to P2 by P1 power k minus 1 by k. Okay, or we can also write P2 by P1 is equal to rho 2 by rho 1 power k, or you can also write T2 by T1 is equal to P2 by P1 power k minus 1. Okay, let's say this is equation number 18. Okay, you just have to separate these variables. So this will become 0, right? So take any of these terms to the other side. So if you just substitute this as 0 for an isentropic process, if this is 0, then we'll get Cp into ln T2 by T1 is equal to R into ln P2 by P1. Okay, then simplify this equation and you'll be getting these forms. Okay, you need to also use this equation, okay, and these equations, and you'll be able to get these forms. Okay, so coming to speed of sound or sonic velocity. So when a minute disturbance develops in a gas, the resulting change in pressure, like whenever there is a disturbance in gas, there will always be change in pressure, right? So the resulting change in pressure propagates in all directions as a compression wave. Okay, so it is also called as pressure wave or longitudinal wave, which we feel as sound. So its propagation velocity is called sonic wave, and the pressure wave is called sound wave. Okay. So consider the small amplitude wave. Let me just draw it here. Let me draw three cases. C P into A. Okay. So consider a small amplitude wave traveling through a conduct at unsteady state conditions. Okay. So in figure A, so let's say this is A, B, and C. Okay. So in figure A, it is moving so that a stationary observer sees an unsteady state motion, and figure B, observer moves with the wave so that the wave is stationary and the steady state flow is observed. Okay. And in figure C, it shows a control volume surrounding the wave, and the pressure is assumed to be create a small differential change in the pressure, temperature, and density, rho, and also velocity of the gas. Okay. So if there's an unsteady state disturbance, if the observer is at steady state conditions or if the observer is stationary, then he'll find the wave to be unsteady state. And if the observer is moving with the velocity of the wave, then he'll find that it is a steady state. And this is a control volume around the wave, and it represents all the changes in the gas, like volume change, pressure change, and temperature change. So if you apply continuity equation to the control volume, then we'll be getting density into area into velocity is equal to change in density into area plus change in C plus dV. So this is 19th equation. So if we neglect higher order terms, we can simplify this as rho dV is equal to minus C into dP. Oh, sorry, this is d rho. Okay, so let's say equation number 20. So the momentum equation in the streamwise direction can be written as rho A minus P plus dP into A is equal to rho A C into C plus dV minus C, right? Huh. So if you simplify this, you'll be getting dP is equal to minus rho C dV. This will become equation number 21. So if you combine continuity equation and momentum equations, it will result in C is equal to square root of dP by d rho. This is 22, equation number 22. So the lower frequency sound waves travel isentropically. So then the equation becomes P by rho power k is equal to constant. This is only for lower frequency sound waves. And if you differentiate this equation, we'll be getting dP by d rho is equal to k into P by rho. Okay, that's equation number 23, and this is 24. Okay, so coming to sound of speed of sound or sonic velocity for such waves can be written as c is equal to square root of. So just substitute dp by d rho as k into p by rho. So we'll be getting k into p by rho, which can be simplified as square root of k into r t. This is equation number 25. So this is only for low frequency waves. So coming to high frequency waves travel isothermally resulting in speed of a sound. So in that case, C will be equal to square root of RT. So that this will become 26. So in other words, the sonic velocity is proportional to the square root of absolute temperature for let's take an example for let's say K is equal to 1.4 and R is equal to 287, which is case of air. Okay. So in that case, C will be equal to 340 meter per second, and this is at 16 degrees centigrade or 289 Kelvin. Okay. So this is how you'll be able to calculate speed of a sound. And let's say if K is the bulk modulus of that particular liquid, and in that case, we already have relation, right? So dP is minus K into dV by V. Okay, so initial equation was K is equal to minus V into dP by dV. So we just simplified in terms of dP. So we just rearrange the terms. So we'll be getting in terms of dP. So this can be written as K into d rho by rho, because rho V is equal to constant, right? Okay, so if you just differentiate this, you'll be getting this equation. So minus dv by v will be equal to d rho by rho. Okay, as an inversely proportional. And we also have a relation that is dp by d rho is equal to k by rho. Okay, so using these equations, we can write c is equal to square root of dp by d rho, right? So you can just substitute the variables and then you can write this as square root of k by rho. Okay, this will be equation number 20. Let's say it's 27, 28, and this will be 29. Okay, so coming to the concept of Mach number. So at stagnation point of a body placed in a uniform flow, the pressure increases using by following this equation, that is del P is equal to rho u square by 2. Okay, so the increased pressure uh, brings about an increased density, and this can be calculated by del rho is equal to del P by c square, which is equation number 31. And the ratio of flow velocity u to the sonic velocity c is called Mach number, which is represented by m is equal to u by c. So m is equal to u by c, which will be equal to 1 by c into. So how do you calculate velocity of flow? It is square root of 2 into del p by rho, which will give us 2 into del rho by rho. This becomes equation number 32. So from this equation, the Mach number m corresponding to density changes of 5% is approximately to be zero point 0.3. Okay, so if the density changes are within 5%, or if it corresponds to 5%, then Mach number is estimated to be zero point 0.3. And for this reason, studies flow can be treated as incompressible flow up to around Mach number of zero point 0.3. And if value of m is less than 1, the flow is considered as subsonic. And if value of m is greater than 1, it is considered supersonic flow. Okay, sorry. So the small magnitude waves are referred to as Mach waves, and they result from a source of sound and needle nose projectiles and the sharp leading edges of supersonic airfoils. Okay, and the large amplitude waves are called shock waves, which emanate from a leading edge of a blunt nosed airfoils. Okay, so we have two types of waves. One is small amplitude waves, and the other one is large amplitude waves. So if these small amplitude waves are they originate from, or they result in these cases, and the large amplitude waves, also called as shock waves, they originate, or they can be seen in these cases, like the blunt-nosed airfoils. Whenever air is going or it comes in contact with this, you can see this. Sorry. So, do you have any doubts until now? If you have, you can unmute yourself and ask me or post them in the chat box as well. Any doubts? If you don't have any doubts, then we can move on to the next topic. Okay, so coming to the next topic that is basic equation of basic equation for one-dimensional compressible flow. So let's consider a continuity equation. So for a constant mass flow of m, so for a constant mass flow of a fluid density rho flowing at velocity u through a cross section A, the continuity equation can be written as m is equal to rho u a, right? Which is equal to constant. So let's say this is equation number 33. Okay. And by logarithmic differentiation, we can write logarithmic differentiation. We can write dp by p, sorry, d rho by rho plus du by u plus dA by a will be 0. So if you differentiate constant, it will become 0, right? So this will become 0. Okay. So Euler equation of motion in steady state equation along streamline gives us integral dp by rho plus half u square will be a constant. So let's say this is equation number 35. Okay. So using adiabatic conditions from equation number 23, we can write p is equal to m into rho power k. Okay. Where m is a constant again, m is equal to constant. And if you derivate this equation and integrate, we'll be getting dp by rho is equal to integral mk into rho power k minus 2 into d rho will be equal to k by k minus 1 into p by rho plus constant. Let's say is equation number 36 and this is 37. Okay. So now coming to Bernoulli's equation for a compressible flow. Sorry, first let's write for incompressible flow and then we'll go to we'll write it well, we'll write the same equation for compressible flow as well. Okay, so let's substitute equation 37 in 35 and we'll be getting k by k minus 1 into p by rho plus half u square will be equal to constant. That is equation number 38. And you can also write this equation as k by k minus 1 into RT plus half u square is equal to constant. Okay, that's equation number 39. Okay, so equation 38 and 39 they correspond to Bernoulli's equation for a incompressible flow. Bernoulli's equation for an incompressible flow. Okay. So the next concept is total temperature, static temperature, and dynamic temperature. You know it. Okay. So if fluid discharges from a very large vessel, okay, so for that U will be equal to U not equal to 0, where naught or the subscript naught represents a state variable in the vessel. So the equation number 39 will give us T naught by T is equal to 1 plus half into 1 by RT into K minus 1 by K into U square, which will be equal to 1 plus K minus 1 by 2 into K minus 1 by 2 into M square. So here M is equal to U by C, this is Mach number, which is equal to U by square root of KRT. Okay, MACH Mach number. Okay, so here T naught is the total temperature, T is a static temperature, and 1 by 2 into 1 by R into K minus 1 by K into U square is dynamic temperature. So the next topic is stagnation and static pressure. Okay, so do you have any doubts until now? Any doubts until now? If you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. If not, we'll move on to the next topic. Okay, so coming to the next topic, that is stagnation and static pressure. So again, we'll go back To equation number, let me just write it down. So let's say this is equation number 40, and we'll use the same equation, that is equation number 40. So that is P naught by P is equal to T naught by T for K by K minus 1. Okay. So this is equal to 1 plus K minus 1 by 2 into M square, which will be M square whole power K by K minus 1. Okay. So stagnation pressure is P naught and the static pressure is P here. Okay. And where M is again Mach number. Okay. So we know Mach number is U by C, which is equal to U by square root of KRT. So next topic is isentropic flow. So which is flow in a pipe and effect of cross-sectional change. So let me just draw a diagram before going into the topic. So let's assume flow in a pipe with gradual sectional change as shown in this figure. Okay, so in this case, equation of continuity or continuity equation can be written as d rho by rho plus du by u plus dA by A will be equal to 0, and momentum equation will become minus dP into A will be equal to A into rho u into du. Okay, and then isentropic equation or isentropic relation will become P is equal to m into rho power K, and sonic velocity will be C is equal to square root of dP by d rho. Okay, and dP by d rho. So let's give numbering to this. Let's say this is 1, 2, 3, and 4, or let's name it as A, B, and C. A, B, C, and D. Okay. So from A, B, and D, we can write from A, B, and D, we can write minus C square into D rho is equal to rho U du is equal to rho U square into du by U. This becomes equation number E. So that means we can write m square into du by u as minus d rho by rho, which will be equal to du by u plus dA by A. This becomes equation number F. So in that case, du by dA will be equal to 1 by m square minus 1 into u by A. This is equation number G. So as per equation number G, if m is less than 1 and du by dA is less than 1, the flow velocity decreases with increased cross-sectional area. And if m is greater than 1 and du by dA is greater than 0, the density decreases at a faster rate than the velocity increases per supersonic flow. So consequently, for mass continuity, in order to increase the flow velocity to the cross-sectional area should increase rather than decrease as for subsonic flow. Okay. So, yeah. So we'll just compare how supersonic and subsonic flow behaves when we are changing few variables. Okay. Low state, then we have subsonic and supersonic convergent and divergent. So we'll see how it behaves. So similarly for supersonic, we have convergent and divergent. Okay. So if you change area, so it becomes divergent, and same thing for supersonic, it becomes divergent. So like divergent and changing velocity. This is opposite behavior and changing density or pressure or temperature. So okay, so coming to isentropic flow, we'll take a case of convergent nozzle. Let me draw the figure first. Let's take the case of convergent nozzle. This is P and this is P naught. Okay, so inside the vessel, these are the conditions P naught, T naught, U naught is equal to 0, and this is rho naught. Okay, so assume a gas of pressure P naught, density rho naught, pressure P naught, density rho naught, temperature T naught, flows from a large vessel through a convergent nozzle into an open air of back pressure, let's say PB. Okay, so isentropically, and this happens isentropically at a velocity u. So you can look at this picture as well. So gas is flowing from vessel, and the initial conditions are P naught, rho naught, T naught, and it is flowing from a vessel to a convergence section. It is flowing from vessel to open air through a convergence section, and the back pressure is PB. So putting P as an outer plane pressure, we can write from equation 38 as K by K minus 1 into P by rho plus 1 by 2 into U square is equal to K by K minus 1 into P naught by rho naught. This becomes equation number H. Okay. So we'll use another equation, that is T is equal to M into rho per K minus 1, which can also be written as MP per K minus 1 by K. Okay. So this is just a relation between rho and P. If you substitute those equations, you will be getting it. M is equal to constant here. This is equation number I. Okay. So equation number H becomes from this U is equal to square root of 2 into K by K minus 1 into P naught by rho naught into 1 minus P by P naught for K minus 1 by K. Okay. And the flow rate becomes M is equal to rho UA, which will be equal to area into, just substitute other variables. You'll be getting 2 by K minus 1. This is the value for U, right? So K by K minus 1 into P naught. And if you take rho into the square root, it will be square rho square, right? And here rho naught and rho square gets cancelled out. So you'll be left with P naught into rho naught into P naught by rho naught whole power 2 by K into 1 minus P by P naught for K minus 1 by K. Okay, this becomes equation number K. Okay. So do you have any doubts until now? These are all mathematical derivations, okay? Mostly from thermodynamics. So we're just trying to manipulate equations and then solve the situation or find the solution for that particular situation. Any doubts? Okay, so coming to critical pressure for maximum flow rate. So what was the equation for flow rate? M is equal to rho UA, which is equal to A into square root of 2 into K by K minus 1 into P naught into rho naught into P naught by rho naught whole power 2 by K into 1 minus P by P naught whole power K minus 1 by K. Okay. So differentiate the above equation with the P by P naught, and if you equate it to 0, we'll be getting. So why do we need to equate it to 0? Because we want maximum flow rate, right? So at maximum, differential will be 0. So that is why just differentiate this entire equation with P by P naught and then equate it to 0. Then you'll be getting dou m by dou by dou P by P naught is equal to 0. So that means P by P naught will be equal to 2 by K plus 1 whole power K by K minus 1. Just apply differential and solve it. So finally you'll be getting this equation. Okay. So M is the maximum for this particular value of P, and the pressure is called critical pressure. So for air, P critical will be 0.528. Okay. So this is how you will be able to calculate critical pressure for maximum flow rate. So coming to choked flow, let me first draw the diagram. Sorry, first let me, yeah, this is the case. Okay. Gas is flowing from a vessel to a through a converging section, and it is flowing through open air. And this is P by P naught. And then we have one more graph that is for mass flow versus P by P naught. 0.528, and this is the maximum value. Okay. This is 1 and this is 0. Okay. So the maximum flow rate, so in this convergent nozzle case, so the maximum flow will occur at P by P naught of point 0.528 as shown in figure, and therefore maximum flow rate will occur at P by P naught value of 0.528. So however, much so if value of PB is higher downstream, okay, so thereafter, however, much the pressure PB in the downstream is lower, the pressure there cannot propagate towards nozzle because it is discharging at sonic velocities. So therefore, the pressure of air in the outlet pane remains P critical. It remains P critical. Okay, P critical. So the mass flow rate does not change, and in this state, the flow is called choke flow. Okay, and then we have critical velocity. So let's just substitute equation number this equation. Okay, what is equation number? Let's say this is L. Equation number L. Oh, sorry, this is let's say equation number L, and this is M. Okay, substitute L into M, and then you'll be getting, and also use P naught by rho naught per K is equal to P by rho K. Use this equation as well. So you'll be getting your critical velocity. That is UC will be equal to square root of K into P by rho, which is again equal to velocity of sound or sonic velocity. Okay. And then we have critical density and critical temperature. So for the condition of m is equal to 1, critical density and critical temperature can be obtained at critical velocity. So we can use this equation, that is rho c by rho naught is equal to 2 by k plus 1 whole power 1 by k minus 1. This should be equal to 0.634. Okay. And Tc by T naught will be equal to 2 by k plus 1, which is equal to 0.833. And at the critical outlet state of m is equal to 1, the critical pressure falls to 52.8% of the pressure in the vessel, while the critical density and the critical temperature respectively decreases by 37% and 17% from those of the vessels. Okay. So coming to the second case, that is convergent and divergent nozzles, also called as de lava nozzle. So we have two sections here, not one. We have a converging section and then a diverging section. And same, we said P naught, T naught, U naught, and rho naught, and this is trying to flow through this nozzle. This is throat of the nozzle, and here PB is the back pressure. Okay. So as shown in the figure, a convergent section followed by a divergent length. Okay. So when back pressure PB outside the nozzle is reduced below P naught, okay, flow is established. Okay. So obviously outer pressure should be lower than the pressure inside the vessel. Only then flow will be there, right? So if you reduce P naught, PB less than P naught, then the flow will be established. And if the fluid flows out through the throat section without reaching the critical pressure, the general behavior is the same as for the incompressible flow. And when the back pressure decreases further, the pressure at the throat section reaches the critical pressure and M is equal to 1 and supersonic flow will start to happen. Okay. So unless the pressure or the back pressure is low enough, supersonic velocity cannot be maintained. Okay. So there are few graphs as well. So I'll not be able to draw them. So but they were already explained in the class. So you can just refer to the class taught by professor. So you'll be able to find it in the class. Okay. The class lecture. I'll not be able to draw it here. Okay. That is fine. Okay. And if the back pressure is not low enough, a shock wave develops after which the flow becomes subsonic and the shock wave moves further away from the divergent length to the exit plane and eventually disappears, giving a perfect expansion. The perfect expansion occurs when A by AC, that is ratio between outlet and the critical throat section. So let's also write the equation for AC by sorry, A by ACT, that is throat. This is outlet section, area of outlet section, and this is area of critical throat section. This should be equal to 2 by k plus 1 to the power 1 by k minus 1 into p naught by p power 1 by k square root of k plus 1 by k minus 1 into 1 minus p naught by p whole power 1 minus k by k. Okay, this becomes okay. Let's leave it there. So this is a ratio of area to the outlet section and critical throat section. Okay. Then coming to the concept of shock wave. Okay. So when air undergoes large and rapid compression, a thin wave of large pressure change is produced. Okay. So this can be observed in let's say jet. Okay. So whenever a jet is flowing or jet is flying, just a second, someone is joining, I guess. Okay. Whenever jet is flying at high speeds, I'm just drawing the initial section. Okay, so the air which is adjacent to the nozzle or the tip of the plane, so it will be undergoing large and rapid compressions. Okay, so as a result of that, you can see a large pressure change is produced. So let's say this is a superjet. Okay, don't mind the drawing. Okay, so let's say the jet is flying at a very high speed. So as a result of this, the air which is adjacent or in contact with the tip, it will be undergoing large and rapid compressions, and because of that, a large pressure change can be observed. And Since the state of gas changes adiabatically, an increased temperature accompanies this increased pressure, and the wave phase at rare propagates faster than the wave phase at the front, which increases the pressure discontinuously. Okay, so such a pressure change or such pressure discontinuity is called a shock wave, which only associated with an increase rather than a reduction in pressure in the flow direction. Okay, so again we have two types of shock waves. One is normal shock wave, the other one is oblique shock wave. Okay, so we'll look at each of them. So first, let's look at normal shock wave. So as I've told you, shock waves are two types. It is normal and oblique. With both with respect to the direction of flow. If a long cylinder is partitioned with cellophane film or aluminum foil to give a pressure difference between the two sections, and the partition is ruptured, a shock wave is developed. So the shock wave in this case is at right angle to the flow and is called a normal shock wave. The tube itself is called shock tube. Okay, so just take a aluminum or a long, sorry, just take a long cylinder and then partition it with a cellophane film or aluminum foil. Okay, I'll just quickly draw a diagram and show it to you. And C2, U2, and M2 is less than 1. Okay, so here A1 will be equal to A2. Okay, at let's say some location dx. Okay, so when this partition is ruptured, a shock wave will be developed. Okay, and this is called normal shock wave, and this tube is called shock tube. So again, you can apply continuity equation, momentum equation, and energy equation as well. So if you apply continuity equation, rho 1 u1 a1 will be equal to rho 2 u2 a2, and momentum equation will become p1 plus rho 1 into u1 square is equal to p2 plus rho 2 u2 square, and energy equation will become u1 square by 2 plus k by k minus 1 into p1 by rho 1 will be equal to u2 square by 2 plus p2 by rho 2. Okay, this is again we have k by k minus 1. Okay, so using these two equations, I forgot the numbering. Okay, so using these two equations, let's say we can write u1 square as p2 minus p1 by rho 2 minus rho 1 into rho 2 by rho 1, and u2 square as P2 minus P1 by rho 2 minus rho 1 into rho 1 by rho 2. Okay. So substituting the values of u1 square and u2 square in this equation, in this equation. So just substitute it. What would be the equation? I'll write down a simplified equation. So u1 by u2 will be equal to rho 2 by rho 1, which should be equal to k plus 1 by k minus 1 into p2 by p1 plus 1 by k plus 1 by k minus 1 plus p2 by p1. Okay. Or we can also write it as t2 by t1 is equal to rho 2 by rho 1 is equal to k plus 1 by k minus 1 into plus p2 by p1. Okay, and we can also write this by k plus 1 by k minus 1 plus p1 by p2. Okay, so this equation shows relationship between pressure, density, temperature ahead of and behind a shock wave. That is, and from the momentum equations, from these two equations, we can also write P2 by P1 is equal to 1 plus 2k by k plus 1 into m1 square minus 1. Okay, and this can also be written as P1 by P2 is equal to 1 plus 2k by k plus 1 into m2 square by m2 square minus 1. So from this you can write m2 square is equal to 2 plus k minus 1 into m1 square by 2k m1 square minus k minus 1. Okay, so this is about normal shock wave, and we also have oblique shock wave. But let me just cover one more concept, that is Fano flow and Rayleigh flow. Okay, just a second, someone is at my door. I'll just be back in a second. Okay, so coming to Fano flow and Rayleigh flow. First, let me draw a diagram for the graph. So this is enthalpy versus entropy. Okay. Okay. So Fano flow, actual flow of compressible fluid in the pipelines and similar context is always affected by the friction between the fixed walls and the fluid. Okay. So it can be adiabatic but not isotropic, isentropic. Such an adiabatic but reversible flow is called Fano flow. Okay. And coming to Rayleigh flow, a flow without friction through a pipe with heat transmission is called Rayleigh flow. Okay. So if you have any doubts until now, you can unmute yourself and ask me. If not, we'll move on to the problem solving session. If you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. If not, we'll move on to problem solving session. Okay, so let's move on to the problem solving session. So coming to the first question, compressibility is higher in case of liquid, solid, gas, or colloidal solution. Compressibility will be high for a gaseous substance. Okay. Coming to second question, incompressible gas flow occurs when the density of air does not change more than 3% between point of interest, more than 5% between points of interest, more than 7% between points of interest, all the above. So when do you consider it to be an incompressible flow? When the density change between two points of interest is less than 3%, right? So that will be 3 per option A. So when the density change does not change more than 3% or the density change within 3%. Okay. So coming to third question, airflow around automobiles is compressible, incompressible. Option C, either A or B. Option D, none of the above. So airflow around automobiles, it will be an example of incompressible flow, right? Option B. So coming to fourth question, an example of a compressible flow is flow through a jet engine, flow in hurricanes, flow around buildings, flow around aircraft during landing. So this is an example of incompressible flow. This is also an example of incompressible flow, and this is also an example of incompressible flow. So all these three are examples of incompressible flows. So option A would be the correct answer. Okay. So coming to fifth question, the specific heat at constant pressure. Sorry, fifth question, right? So velocity of a pressure wave propagating in a fluid is directly proportional to K power 1.5, K square, K power zero point 0.5. It will be proportional to square root of K, which is K power zero point 0.5. Okay. Coming to sixth question, the specific heat at constant pressure Cp for a real gas is always dash the specific heat at constant volume greater than, smaller than, equal to all the above. So it will always be greater than because Cp minus Cv is equal to R, right? So R is a positive quantity. So Cp minus Cv, Cp will always be greater than Cv at constant pressure. Okay. So coming to seventh question, three fluids 1, 2, and 3 have bulk moduli of K1, K2, and K3 respectively. If K1 is greater than K2 greater than K3, which liquid will be having highest compressibility? So we know compressibility is equal to 1 by K, right? So if the gas should be highly compressible or if the liquid should be highly compressible, then it should have lower bulk modulus, right? So which gas has lower bulk modulus? K3 is lowest when compared to other two bulk moduli, right? So that means third fluid is third fluid is highly compressible. So that will be option C, right? So coming to eighth question, the speed of sound or sonic velocity for sound wave is proportional to t power zero point 0.5, t square or 1 by t. So it will be proportional to square root of t, which is also t power zero point 0.5, right? This is again conceptual question. So coming to ninth question, steady state flow can be treated as incompressible flow up to Mach number 1.3, 10, 3. So it can be considered as incompressible flow till zero point 0.3 Mach number, right? This is option B. Okay. So that is it. If you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. If not, we can end this session. Okay, any doubts? If you have any doubts, either in the problems section or in the theory part, you can unmute yourself and ask me. So thank you everyone. Thank you for attending the session. Let's meet on next Tuesday. Thank you.